like I said, you cannot come to look at unsymmetrical faults if you haven't understood symmetrical components. So take your time, go through what I've explained, rewatch that many times so that you can understand those equations and you can have a clear understanding of what we are talking about of the sequences or sequence components. Now, when we come to unsymmetrical faults, they are called unsymmetrical faults because they are not symmetrical, they are not balanced. This means that this fault can give rise to unsymmetrical fault currents, unequal in other words. That is unequal currents in the lines with unequal phase displacement, meaning that it is going to create, just as we looked at in the initial stage, where the phase angles are going to be unequal. They are not going to be all 120 degrees because of the fault. And then equally, the phase magnitudes are also going to be unequal. So you've got the magnitudes to be unequal and the phase angles being unequal. And that is what we call unsymmetrical faults. These faults may occur in most cases as short circuits in a three-phase system where you have the occurrence of a fault between a line to ground, which is this case. This is a line to ground fault where you have a line bolting to ground. Okay? Once the line connects to ground, you've got a line to ground fault. You can equally have another scenario, which is a line-to-line fault. This is when two conductors are connected somehow by either a tree falling on them, either anything that causes that fault can happen and bring about what we call a line-to-line fault. And then the third scenario is what we call a double line to ground fault, that is LLG, so double line to ground fault. Okay, and this is the third case scenario. The fourth case is what we looked at in the initial, I think if you go to my channel, you can see the symmetrical faults have been discussed already. And in that section, we looked at using the reactances method, using the reactance method. In this case, we'll try to look at the Z-bus approach. Okay, so these are the three types of faults that you experience in the unsymmetrical occurrences, where you have the line to ground fault, line to line fault, and the line to line to ground fault. Now, as I mentioned also, we do have other faults such as the open circuit fault. This is where a conductor cuts, or you can have one line in the transmission line lose a phase. So if you have got three transmission lines and then you have, so if this is a tower, you have a cut of this line. And if you have this line lose its phase, so if this line cuts and drops, that is an open, we call that an open circuit fault. Okay, so this creates an open circuit here. You can equally have two lines develop a fault. Maybe a tree falls on two lines and drops both lines. Then you have got two conductors open fault, which breaks can stop the breaker. The breaker can open to protect the system. And if we have an unsymmetrical fault occur in a balanced system, then the sequence networks are interconnected only at the fault location. And this is what we are going to look at just now. So for us to make the unsymmetrical faults, there are following assumptions. There are some assumptions that we take. One is that the system operates under balanced steady-state conditions before the fault occurs. This means that the zero, positive, and negative sequence networks are uncoupled before the fault occurs. The next condition is that the pre-fault load current is neglected, meaning it is zero. And because of this, the positive sequence internal voltages of all machines are equal to the pre-fault voltage VF. And the third assumption is that all resistances and shunt admittances for the transformers, transmission lines are neglected. So these are the assumptions that we take to understand and look at the unsymmetrical three-phase faults, or the asymmetrical, you can also call them asymmetrical three-phase faults. Okay, so this is what we mentioned, that if the sequence components before the fault or in the pre-fault stage, when the system is balanced, you've got the zero sequence, the positive sequence, and the negative sequence are all unconnected. As you can see, all these equivalent circuits are unconnected. They only get connected at the point of the fault. Okay? They only get connected at the point of the fault. So in the pre-fault stage, they are all unconnected, and this is what you have. Then this is now a scenario where we have a line to ground fault, a single line to ground fault. When it occurs in a three-phase system with a zero fault impedance, as you can see, the fault impedance is zero. What you have, since the fault impedance is zero, what you're going to have is that VA is going to be zero, IB is going to be zero, and IC is going to be zero, since the load currents are neglected. And then we can convert these to equivalent conditions in symmetrical components, meaning VA is equal to VA0 plus VA1 plus VA2 equal to 0, and our currents, therefore, can be determined from, that is the IA0, which is a zero component current, IA1, IA2. IA1 is the positive sequence current, the negative sequence current is going to be 1/3 the transformation matrix multiplied by the transformation matrix, which is, in this case, is our A inverse, that is the inverse of the transformation matrix, multiplied by A, which, as we know, in the line to ground, we have IB equal to 0 and IC equal to 0. Therefore, giving us IA0 to be equal to IA1, which is equal to IA2, and is equal to IA/3. And we could use now the network equations and in the symmetrical components to give us the result for the fault current IF to be equal to A. So in this case, we have our symmetrical voltages to be as follows. These are sequence components: VA0, VA1, VA2 to be equal to 0, VF, 0, minus, and then we have the impedances, that is the zero component sequence impedance, Z0, the positive sequence Z1, the negative sequence Z2, and these are impedances. And then this will multiply by the currents, since these currents are already determined as IA over 3, IA over 3, IA over 3. Which gives us now, if we simplify from here, IA0 plus IA1 plus IA2 will give us 0, which is equivalent to now Z0 coming from this equation, Z0 IA3 plus VF, which is the fault voltage, minus Z1 IA over 3 minus Z2 IA over 3. If we simplify this, we get now with our IF equal to IA, then we can replace in our equation, and our IF therefore is equal to, this is the fault current, is equal to 3VF Z1 plus Z2 plus Z3. So we are adding all the component impedances in this case, multiplied by 3VF. And that is how we can determine the fault current for a line to ground fault with a zero fault impedance. Okay, so in this case, this is what you have. If we consider that we have zero fault impedance, so you have your Z1, Z2, Z0, and IA1, IA2, IA0 are equal. So the circuit, as you can see, is basically a closed loop circuit where your current is going to be simply one current flowing in this circuit. Simply one current flowing in the circuit. And this is the connection of the sequence network for the line to ground fault with the impedance, fault impedance being 0. Okay, the fault impedance being 0. Now, we can include the fault impedance here, which, as you can see, so if we have the fault impedance, we have the ZF, then there are a few changes that occur in the calculation. We have to add the ZF to now the impedances that we are considering. And in that case, like I said, what happens now if we've got the impedance considered, then our IA VA is equal to IA ZF, and all our voltage elements added together, if we get the current multiplied by the sum of the currents by the impedance that we have, the fault impedance. Therefore, we end up having an additional 3Z ZF as the fault current in the equation of the fault current, sorry. In the determination of the fault current, we have the 3ZF added for us to determine the solution. And this is what we mentioned. So if we have a fault, line to ground fault, so then we have, in this case, we have the impedance that is added to the system. This is that impedance. And then we've got this line connected to ground. So as we said, the sequence components are going to be connected or linked based on the fault that we have in the system. Okay, and the ZF is considered the earth path, or the path to earth, and each part is considered to be added to the calculation for the fault current. This is an image captured from a relay, a numerical relay. This is what transpires when you have a line to ground fault. So the phase that is affected in this case obtains a very huge current. As you can see from this diagram, you've got phase A here becoming an extremely large current as compared to the normal operation of the circuit. So this is the stage, this is at this point where we develop the fault. So this is when the fault occurs. So at this stage, you have the fault occur at this point, and you can see that this phase goes off balance, whereas the two other phases remain balanced. But as you saw from the equations, these currents will also diminish to almost zero in the system, in a practical system. For the voltages, what you are going to experience is that the faulted phase is going to reduce. This voltage is going to drop drastically, while the current increases, the voltage is going to drop drastically to a very, very small value, as you can see in here from this relay, numerical relay, as picked up by the numerical relay. Okay, so when we have the line to ground fault, again, what we are experiencing is that at this stage we have got the fault impedance is equal to 0, ZF is equal to 0, when you consider the two lines connecting, bonding together, which is B and C, and what we experience is our IA equal to 0, our VB will be equal to VC. These two are going to be equal, and our currents are going to simply be the opposite. That is, IB is going to be equal to minus IC. And we can get the sequence component elements of the currents here as IA0, IA1, IA2. That's the singular matrix to be equal to 1 over 3. We've got the inverse of the transformation matrix A here, multiplied by IA, which we know is going to drop to 0, and then IB and IC, which is a minus of IB. So from simplifying this, we get our IA0 to be equal to 0, our IA1 to be equal to minus IA2, our VB equal to VC. Okay, and then since we know our VB is equal to VC, we can substitute in this equation and determine our components values. From there, we are now able to determine our current. So if we look at the connection of the two lines, what we experience is that we've got that line 1 and then line 2, and the zero sequence element is going to be disconnected from the system. So what we have now is that this circuit gives us VF, the two impedances, Z1 and Z2, and we are able to determine from this the current IA1, which is in the opposite direction to IA2. So IA1 is equal to IA2, which is equal to VF over Z1 plus Z2, considering the fact that our IA0 is equal to 0. So this is why this is separated from the connection, because this is equal to 0. Okay, and this is our fault current, which we can determine from this particular example for the line-to-line fault. So if we have now an impedance that appears in the fault between the line-to-line, it could be included as half ZF in each phase B and C, and this will now lead us to have the following sequence. So V1 minus V2 will give us ZF over I1, and the fault conditions in sequence domain, what we are going to have now is I0 equal to 0, I2 equal to minus I1, and V1 minus V2 will give us ZF I1. So the fault current in this case will be equal to, we are simply adding a component of, we're adding the impedance, the fault impedance to this equation for us to obtain VF over Z1 plus Z2 plus ZF. Okay, so you must understand very clearly here that what we mean by V1 and V2, this is the voltage, that is the positive sequence voltage, and this is the negative sequence. So this is the positive sequence voltage, this is the negative sequence voltage. Equally, this is the positive sequence impedance, and this is the negative sequence impedance. Okay, and this is the fault impedance. So if we are saying, if between the fault of the line, instead of a fault simply occurring like so, we have a fault that develops an impedance in between, which is the ZF. So this is a bolted fault where there's no impedance, as the scenario we looked at first, and this is now the scenario where when there's a fault, there's an impedance that is generated in between, and that impedance is the ZF. When we incorporate it into our fault current, IF, which is going to be equal to I1, which is going to be negative I2, it's simply going to be this. So this is the positive sequence current, the negative sequence current. That is the meaning of the 1 and the 2. So this is what occurs as recorded by a relay. When a fault occurs in a line-to-line, we experience that those two lines are going to have extremely large currents in the opposite, exactly in the opposite. That's why you have, in this case, IA or I1 equal to the negative of I2. So these two currents are extremely large, and whereas the other current will be almost zero, and the voltages for the two phases are also going to drop drastically to a very minimal value of voltage, as seen from this diagram. So just like in the last case, as I explained, we experience the fault occurs at this stage. So this is F, that is the point of the fault, and then we have got this behavior of the currents and this behavior of the voltages, where the currents the magnitude become extremely large, whereas the voltages become extremely small for those two phases. Coming to the last portion of the fault, which is the line-to-line to ground fault, with the fault impedance being equal to 0. During the fault, what we experience is that the phase current in A is going to drop to almost 0. In B, the voltage in B is going to be equal to voltage in C, which is going to be 0. So it's going to drop to 0. This leaves us with the sequence component currents, IA0 plus IA1 plus IA2, and then the condition now where VA0 equal to VA1 equal to VA2 correspond to all the three sequence networks that become connected in parallel, as you can see here. So these elements become connected in parallel. You've got the zero sequence, the negative sequence, and the positive sequence getting connected in parallel, and therefore we are now able to determine our positive sequence fault current, which is IF or 1, to be equal to VF from this, and then we have these parallel impedances Z2 and Z0 will be added in parallel and then added to Z1, as you can see. So Z2 is parallel to Z0. This is basically saying we have Z2, Z0 plus over Z2 plus Z0. This is what we mean when we say these two are parallel. This is this component here. And the negative and zero sequence fault currents equally are going to be as follows, where you have the I2, which is coming from there, is going to be minus I1 multiplied by Z0 over Z0 plus Z2, meaning is this component here. The impedances are simply going to add up. And then for I0, you've got minus I1 Z2 over Z0 plus Z2. That is this and this. Okay. So these are the fault currents that you are going to solve when you have line-to-line to ground fault. And if we add the component of the impedance, the fault impedance ZF, then what we get is that our VB is equal to ZF IA plus IB, which transforms the domain sequence now. We get A0 plus A1 plus A2 to be 0. Since VC is equal to VB, what we get now is that our IA V0 plus A1 AV1 plus A squared V2 is going to be equal to V0 plus A squared V1 plus A V2. So this is because we are saying VC equal to VB, and these are the components that we get, which we can simplify from there to get A squared minus A V2 to be equal to A squared minus A V1. And so the fault conditions, therefore, are going to give us this aspect of our V0 minus V1 here to be equal to 3ZF multiplied by I0. Remember that V1 equal to V2 in this case. So therefore, when we incorporate the component of 3ZF included in series with the zero sequence network, if you remember, we had that where we had the parallel elements, VF, we had Z1, we had Z2, we had Z0, and we said all the three are connected in parallel during the fault. So this is Z1, Z2, Z0, this is VF. Then what happens is that in series to the zero sequence network, we add another impedance. We add another impedance, which is now the 3ZF. So we have our 3ZF added in this network. Okay, so you now have the Z2 parallel to the sum of these two impedances. Okay, where you have Z2 I1 is equal to Z1 plus Z2, which is now parallel to Z0 plus 3ZF, which is this component here. And this is what happens. And when you simplify that, you get this equation there. And then using the current divider rule, you get the negative and the zero sequence fault currents as shown below. Okay, so then the line to ground fault, when it occurs, this is what we experience in a similar fashion like we saw in the line to line fault. You have the two currents that are going to be extremely large, but not opposite to each other. In this case, they're almost in phase, but extremely large. And then the other current is going to drop to zero. Equally here, the voltages are going to drop to almost zero. The voltages in the phases where there is the fault. So this is what happens. And now, in the next video, I'm going to explain to you how we solve and look at a few examples of solving the fault analysis based on the asymmetrical or unsymmetrical system. Thank you.